Okay, hello everyone in a new video. In this one we are going to start a new chapter, which is chapter number 9, Equilibrium of a Body, in the third unit of mechanics. And let me start by the first section, which is the condition of equilibrium. So in order to explain this condition, let me have the following solid given to be S, acted upon the following two forces. Then let's suppose F1 is acting vertically upward like this, and we have another force which is acting vertically downward like this. So let me say that this is the force F1 and this is the force F2, both of them acting at the point G. So here I didn't mention, or we can suppose that G is the center of gravity, but I'm not putting this as a condition. And let me say that an object S is said to be at equilibrium under the action of two forces, if it is at rest. So what do we mean by the equilibrium? So notice that the first part of this word is coming from the equality or equal under the action of two forces if it is at rest. And by at rest or at equilibrium means that this is not moving. In other words, the action of the force F1 must cancel the action of the force F2. So in this case, so how can we describe this at the level of the properties of the forces? We say that F1 and F2 have the same line of action, opposite direction, and same magnitude. Notice that I have represented F1 and F2 in a manner that both of them have the same magnitude, but we need to express this mathematically at the level of an equation. And here it's not important whether both forces are applied at the same point. So the point of application, it's not necessary to be common for both forces, but we will not enter into discussion regarding the point of application. So we are just only concerned about the line of action, the direction, and the magnitude. Then let me say at equilibrium, and this is known as the condition of equilibrium. Or even the vector relation at equilibrium. And we are referring to the following relation, which is given by, then what are the forces acting on the solid S? We have the force F1 and the force F2, then the sum of these forces must add up to 0. Then on the left hand side of this equation we have the sum of forces acting on the solid S, and in this case the sum of forces adds up to 0. The 0 factor indicates that the solid S is at equilibrium, and also we can read this equation in the following form. If we drag this force to the right hand side, so what we will have is that F1 is equal to 0 vector minus F2 vector, which is simply equal to minus F2 vector. So we have that F1 vector is equal to minus F2 vector. So we can say or F1 is equal to minus F2 vector. So let me repeat this equation. We read it in the following way. The action of the forces F1 and F2 cancel out to give us the 0 vector. The 0 vector indicates the equilibrium condition, which means that the solid S is not moving, and we don't forget vectors on F1, F2 as well as the 0. As for this equation, we read it in the following way. Both forces F1 and F2 have the same line of action, opposite direction for the minus sign, and same magnitude. So in this case we can say in magnitude we have that F1 is equal to F2. So notice that whenever we are discussing the magnitude, we drop down the vectors and we remove the minus sign, so we have that F1 is equal to F2 in magnitude. And in general, for the equilibrium condition, we have the following to be true. Then let me say in this case, we have that F1 and F2 vectors have the same line of action, then in this case both forces have the same line of action, which is vertical. Now F1 and F2 have opposite directions, and as we have mentioned here, that they have the same magnitude. Then whenever two forces acting on the same body and this body is at equilibrium, this directly means that both forces have the same line of action, opposite direction, and the same magnitude. So all of these three conditions must hold at the same time. Then we can directly write the following important note. So if the forces F1 and F2 have, so not the same line of action, different line of action, or not necessarily just the different line of action, but also different direction, then let me say or different direction, or even different magnitudes, So in the case where F1 and F2, they don't have the same line of action, different line of action, or even different direction. And here let me be clear that there is a difference between the opposite and the different. So different directions may be up and right, whereas opposite directions may be, so they are given by, for example, up and down, right or left. So these two statements, opposite and different, they are not the same. So different line of action or different direction or even different magnitude, then in this case we can deduce that then the object S is not at equilibrium. And let me solve the following exercise as a direct application on what I have just explained. Then section number 2, exercise number 1, they are telling me for each of the following documents, the object is submitted to two forces F1 and F2. Indicate whether the object is in equilibrium or no, justify. So it's important that we are only discussing a solid S being subjected only to two forces. So this is not the case of 3 forces, 4 forces, etc. It's just only the case of 2 forces. Let me start by document 1. Then we need to state if the object is at equilibrium or no. It is at equilibrium when both forces have the same line of action, opposite direction, and same magnitude. So notice that in this case F1 and F2 have the same line of action, which is vertical. They have opposite directions, one of them is up, the other is down, whereas the magnitude is not the same. So in this case, the solid S is not at equilibrium, so it will move downward. Then let's say since don't have the same magnitude, or let me say they are not equal in magnitude. And this is because 2 newtons is different than 3 newtons. Then the object is not at equilibrium. And recall that what does the word equilibrium means? It is at rest, it is not moving. Now as for document 2, so this is directly not at equilibrium because in order for the object to be at equilibrium, both forces must have the same line of action. So notice that here the line of action is not the same. This is horizontal where this is a vertical. Okay, so as for document 2, since F1 and F2 don't have the same line of action. And this is because, so let me write here the same line of and this is because horizontal is different than vertical, then the object is not at equilibrium. Now as for document 3, so notice that in this case also in document 3 both forces don't have the same line of action. This is oblique where this is vertical, so the object is not at equilibrium. Then let me say since F1 and F2 don't have the same line of action. And this is because oblique is different than vertical. Then the object is not at equilibrium. As for the final document, document 4, so notice that in this case the forces F1 and F2 have the same line of action, which is vertical. Now the point of application is not important, they have different point of applications, and this is what I have mentioned in the beginning of this part. As for the direction, they are opposite because F1 is upward and F2 is downward. And as for the magnitude here, the magnitudes are not given, we have the length of the vector. So if the length of the vector are the same and they are represented using the same scale, which means that F1 and F2 are equal in magnitude. Then let's say so it is at equilibrium, since F1 and F2 have the same line of action, which is vertical, opposite direction, up and down, and same magnitude, which is corresponding for 5 centimeters, represented at a certain scale, then the object it is at equilibrium. And let's move to the next exercise, which is exercise number 2. They are telling me a solid S having the shape of a cube, A is equal to 10 centimeters. So this solid S is being classified as a regular shape, which is a cube, and its side is given by 10 centimeters, which means that its volume can be calculated via the formula V is equal A to the power 3. A is equal to 10 centimeters. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. So it's given by 10 divided by 100, which is 0.1 meters. It's placed on a very smooth inclined plane, negligible friction. So here, friction between the surface of contact between S and the inclined plane is neglected. So here the friction is neglected, as shown in document 1. The density of S is rho is equal to 2000 kilogram per meter cube. So rho is equal to 2000 kilogram per meter cube. So the moment we have the density and we have the volume, so we can calculate the mass. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Number 1, they are asking us to calculate the volume V of S. We know that V, because it is classified as a regular shape, is given by A to the power 3, which is 0.1 to the power 3. Plugging this on the calculator, we always use the value which is the SI, not the given one. It is given by 1 times 10 to the power minus 3. Since the side is expressed in the SI, so the volume V will be expressed in the SI, which is meter cube. So the volume V is given by 1 times 10 to the power minus 3 meter cube. Now as for number 2, they are telling us show that the mass of S is M is equal to 2 kilograms. So for example, one of the methods to calculate the mass from the formula using weight is equal to M multiplied by G. But here in this case, weight must be given. We don't have the weight. However, we know the density, we know the volume. So mass can be calculated using the following formula. Then constructing the triangle, so here we have divide, so here we can, so m will be at the top, rho and v at the bottom, putting our hand over m, then m is given by rho multiplied by v. The value of rho is given by 2000 in the SI, and the value of the volume in the SI is given by 1 times 10 to the power minus 3. And plugging this on the calculator, then the mass is given by 2. Since this is expressed in the SI, this is in the SI, so the value of m will be in the SI, which is kilogram. Notice that here the density is given by kilogram per meter cube, and this is meter cube, so eventually they cancel with each other and the unit will be kilogram. So the mass in this case is given by 2 kilograms. And now in number 3 they are asking us to calculate the value of the weight, and by the value it means the magnitude. We know that the magnitude can be directly calculated from this formula. Weight is equal to m multiplied by g. The value of m is 2, and the value of g is given by 10. And plugging this on the calculator, the value of w is given by 20. Since both m and g are expressed in the SI, so the value of w will be in the SI, which is in newtons. And you can check that by, so 2 is kilograms and this is newton per kilogram. Notice that kilogram cancels out with kilogram, so this is given by newtons. So the weight is given by 20 newtons. Now in number 4, they are telling us give the line of action and the direction of W. So we know always the first 3 properties of the weight are fixed and they are scene independent. So the point of application will always be the center of gravity G, the line of action vertical, and the direction is downward independent of the scene. So now they are asking us about the line of action and the direction. With no exception, the line of action is given by vertical, whereas the direction is given by downward. Let me make some space here. Now in number 5, they are asking us to redraw document 1 and represent on it W using the scale 2 centimeters, 10 newtons. So first, let's redraw document 1. Now the details of this document is not important, so we expect that this is good. Now in order to represent the weight, we need to determine the length of this vector. So what we know is that the magnitude of the weight is given by 20 newtons. So in order to determine the length of the weight, we need to use the following scale. So notice that in this case, this is not a scale because this is 2 centimeters. So we need to transform this to a scale. So given 2 centimeters corresponds to 10 newtons, then dividing both sides by this number, which is 2. So then the scale is given by 1 centimeter corresponds to 5 newtons. Now, although if one used the following scale, the answer would be the same, but it's a good habit to convert this to a unit of length, which is given by 1. And now we are ready to use this scale in order to represent this vector, which is the vector W of magnitude 20 newtons. Then 20 newtons under 5, what is the length of this vector? Now if we cross multiply, then 20 multiplied by 1 divided by 5, this is equal to 4. Because it is under centimeters, then its length is given by 4 centimeters. And we know that always The weight is represented from the center of gravity G. Then this is almost 4 centimeters. So this one here, it's 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. So this is the weight W. And this is the point G, and this is 4 centimeters, corresponding to 20 newtons according to this scale. Now in number 6, they are telling me S is submitted to its weight W and another force, and this is straightforward. So let's recall that whenever we have a mass, we have weight. Whenever we have a string, we have a tension. Whenever we have a support or an inclined plane, we have the normal reaction. And whenever we have an electricity, we have an electric force. Whenever we have magnetism or magnet, we have the magnetic force. So here in this case, we have this support, which is the inclined plane. They are asking me, give the name of this force. So the name of this force will be the normal reaction. And they are telling me and specify for each of them whether it's a contact force or force acting from a distance. Now if we look carefully at the question, they are telling me for each of them, and they are referring to both forces, the normal reaction and the weight, and we need to classify these forces. So let's start by the weight. It is acting from a distance. We know that the only 3 forces that act from a distance are the weight, the electric, the magnetic, and all other forces are classified as contact forces, and in particular the normal reaction. So the normal reaction is considered to be contact force. Now they are asking us, number 7, S is not at rest to justify. So in other words, they are asking us why S is not at equilibrium. Then not at rest, it means not at equilibrium. So we need to justify why S is not at equilibrium. And then in order to do so, we need to compare the properties of W and N. So notice that here, if we need to represent the normal reaction will be like this. Let me represent it here. Although they didn't ask me about the representation of N, but in order to understand the question, we will represent N. So N is a contact force, then it will be represented at the point of contact between the solid and the inclined plane. Let's say that this is the point A. So this is the normal reaction. Now in order to determine whether S is at equilibrium or no, it is sufficient to compare the properties of N and W. We are not talking about the point of application, we are talking about the line of action, the direction, and the magnitude. So we require that in order for S to be at equilibrium, that both forces must have the same line of action, opposite direction, and same magnitude. And here one can directly notice, because that there is only 2 forces acting on the solid S, and this is oblique and this is vertical, so they don't have the same line of action. And this is because oblique. So the normal reaction has a direction which is oblique, whereas the weight has a direction which is vertical. So oblique is different than vertical. Then S is not at rest, which means it is not at equilibrium. And now let's move to the final exercise for this part, which is exercise number 3. They are telling me a solid S of center of gravity G is suspended from a string A, and the other end of the string is fixed to a support. The solid S has a density ρ, so the density is given in the SI, and of volume V, so we have the density and we have the volume. We can directly determine the mass. Determining the mass, we can deduce the value of W given G. The solid S is in equilibrium under the action of the weight and the tension T, so we have the weight and the tension. Take G is equal to 10 newtons per kilogram, which means that this experiment is being performed on the surface of the Earth. In number 1, they are asking me to draw a diagram consisting of S, the string, and the support. So let's recall that here a solid S of center of gravity G. So they didn't specify the shape of the solid. I will take the solid to be circular, a perfect circle. Of center of gravity G. This is the solid S. Is suspended from a string at A, so this is the point A, and the string is fixed to a support like this. Then this is the diagram for number 1. Now this shading here is not important. This just only to indicate that there is nothing above the support. We are not interested what is above the support. Now in number 2, they are telling me to classify the forces W and T, and by the classification it means that we need to specify which of these forces it is acting at a distance or contact force. We know that the only 3 forces act at a distance are the weight, the electric, the magnetic, and all other forces are contact forces, and in particular the tension T. So the weight is acting at a distance, and all other forces are contact forces, and in particular the tension T. So always the classification is to specify whether the force is acting at a distance or a contact force. Now here in number 3, we need to list the point of application, the direction, and the line of action of these forces. Let me start by the weight W. Then for each of these forces, we need to specify the point of application, the direction, and the line of action. But here notice that we need to specify them in the Pilgrim order, so we will start with the point of application, the line of action, then the direction, and not in the following order. So then let me start by the weight W. So because this force is classified as force acting from a distance, then the point of application will be the center of gravity G. Now the line of action is vertical and the direction is downward. So always the first 3 properties of the weight are always fixed like this. Now we need to determine the other properties of the tension. So as for the point of application of the tension, because the tension is a contact force, then the point of application will be the point of contact between 2 bodies, which is the string and the solid S. In this case, it is the point of contact A. Now what about the line of action of the tension and the direction? We know that the line of action is along the string, but now because we know that the solid S is in equilibrium, so the line of action and the direction of the tension, they will have the same line of action, which is the vertical. As for the direction, it will be opposite. So if this is downward, then the direction here will be upward. So here we can see that the equilibrium condition is very effective in determining the properties of the other force. So the line of action is vertical, the direction is upward. So this is it for number 3. They are telling us in number 4, calculate the mass m of S and deduce its weight. So the mass can be determined from the density of the volume. We know that rho is equal to m over v. So we are interested in determining the value of m, constructing the triangle of this formula here because we have divide, then rho then will be at the bottom, m at the top, v here, putting our hand over m. Then m is given by rho multiplied by v. The value of rho is given by 2000. And the value of v is given by 1.5 times 10 to the power minus 3. Plugging this on the calculator, then the value of m is given by 3. Since both rho and v are expressed in the SI, so the value of m will be in the SI, which is kilograms. Then the mass is given by 3 kilograms. And the moment we have determined the mass, we can directly deduce the weight, and deduce it means that we use the previous part. In the previous part, we have determined the mass, we know the value of g. So weight is equal to m multiplied by g, then 3 multiplied by 10. This is equal to 30. Since both m and g are expressed in the SI, so the value of w will be in the SI, which is in newtons. So weight is equal to 30 newtons. Now in number 5, they are telling us to determine write down the condition of equilibrium. So this part consists of several parts. Let me start by the first one, which is writing down the condition of equilibrium. Then whenever they ask us to write the condition of equilibrium or the vector relation, we always start by the following title, which is at equilibrium. And on the left, so here we have equal. On the left, we will always write the sum of forces acting on the solid S, and in this case they are given by the weight and the tension. And on the other side of this equation, we will write the zero vector corresponding for the condition of equilibrium. We don't forget the vectors on each of these three quantities. And now dragging the tension to the right hand side, it will be w vector is equal to 0 vector minus t vector, which is simply w vector is equal to minus t vector. So here we have the w is equal to minus t vector. So the first equation, we read it in the following way, that the sum of forces acting on the solid S cancel each other to give us the 0 vector. Whereas the second equation, we read it in the following way: weight and tension have the same line of action, opposite direction, and same magnitude. And they are telling me to prove the following relation, that t is equal to m times g. In other words, we need to prove that t is equal to w. And this is done, so here we don't have vectors, which means that we are concerned about the magnitudes. And this is done by taking only the magnitude of this relation. So we can say in magnitude. So now in magnitude, we drop down the vectors and we remove the minus sign. So we have that w is equal to t. But we know that w is equal to m times g, which means that mg is equal to t. In other words, t is equal to m multiplied by g. So this is a new relation that relates the tension, the mass, and G, and for this relation we can construct the following triangle here. Because we have multiply, then T will be at the top, M and G at the bottom. And they are telling me to deduce the value of T. So here we can say, also we can say that W is equal to T, but W is equal to 30 newtons, then T is also equal to 30 newtons. Okay, which is simply from this relation that W is equal to T is equal to 30 newtons. But I have written this relation again on a new line. Then let me write here above that we have the tension is equal to 30 newtons, as well as for the weight it's given by 30 newtons, and as well as for the formula of the tension is given by M multiplied by G. Now in number 6 they are telling me on the drawn diagram represent W and T using the scale 3 centimeters 30 newtons, and by represent it means that we need to draw the forces W and T. So we have the magnitudes of these forces. In order to draw them we need to determine the length. The length can be determined using a scale. This actually is not a scale because 3 centimeters must be converted to 1. Knowing that each 3 centimeters corresponds to 30 newtons, dividing both sides by 3, then this is given by 1 centimeter corresponds to 10. I know that using this as a scale from the early beginning would give us the same result, which is given by 3 centimeters as we shall see. But it's always convenient to convert this to a scale because our rulers are graduated by, so divisions in our ruler are divided by 1 centimeter and not 3. So now we are interested in determining the length of this vector, which is 30. Then now if we cross multiply, then 30 multiplied by 1 divided by 10. This is equal to 3. So because it is under centimeters, then this is given by centimeters. So this is the length of the tension T, and it's the same for the weight. We will not repeat the calculation. Now it's left to represent these forces. So we know that the weight is acting on the center of gravity G, so it must be exactly vertically downward, starting from the point G 3 centimeters like this. The arrow here must indicate that it is acting vertically downward. The length of this vector is 3 centimeters, corresponding for 30 newtons according to this scale, and the name of this force is the weight W. As for the tension T, we know it's being acted at the point A vertically upward along the string. So here the divisions, in order to stress that this is 1 centimeter, this is 1 centimeter, this is 1 centimeter, which add up to 3 centimeters, corresponding to 30 newtons according to this scale, and the name of the vector is the tension T. And as you can notice now, referring to this diagram, it's clear that both the solid S is at equilibrium because the forces T and W have the same line of action, same magnitude, which is the same length, and same line of action, opposite directions, and same magnitude. Now in number 7 they are telling us, knowing that the string can withstand a maximum tension of T max is 25 newtons, show that the string will cut. So how come the string will cut? We have T max, whereas the tension due to this weight will be 30 newtons. So this can be done by comparison. Since T max, or let me say since T 30 newtons, which is greater than T max, or let me say since the applied tension is greater than the maximum tension that the string can withstand. And this is because 30 newtons is greater than 25 newtons. And now we rephrase the following statement, then the string will cut. And now as for number 8, they are telling us to calculate the maximum mass, max, that can be attached to the string without being cut. So we are interested in calculating max. So notice that max is related to the tension via the following formula. Let me make some space here. So now we know that T is equal to M multiplied by G. So how we determine M max, knowing that we have T max? So we are interested in determining the value of M. We know that M, for example, can be calculated using W, because weight is equal to M multiplied by G. But because we have T max, so T max will be related to the maximum mass, knowing that also the weight is equal to the tension. So whether we use this formula or we use the following formula, it is exactly the same, because the weight in this case is equal to the tension. But here I'm using M max because we know T max. Now constructing the triangle of this formula, here because we have multiplied and T will be at the top, M and G at the bottom, we are interested in determining the maximum mass, which is given by T over G. Since this carry the label max, then this will carry the label max. And T max is given by 25 and G is given by 10. Plugging this on the calculator, then M max is given by 2.5. Since everything is expressed in the SI, T max and G, then the value of M max will be in the SI, which is kilograms. Then the maximum mass, in this case that the string can withstand, is given by 2.5 kilograms. And this is reasonable. Why? Because if you compare the original mass, which is given by, we have determined the mass in this case, and it was given by 3 kilograms. Notice that in this case, the applied mass is also greater than the maximum mass, which reflects the fact that the applied tension coming from the applied weight is greater than the maximum tension that the string can withstand. So that's it for me in this video, guys. In the next part, part 2, we will explain Hooke's law.